Okay, good morning, everyone. Let's get started. Thanks for braving the cold to come in and talk about evolutionary robotics. Speaking of evolutionary robotics, where were we, where are we, and where are we going? I misspoke last time. Grad students, you're working on assignments A5 and A6. That's motors and refactoring, not motors and neurons. Anything I say or don't say in class is overridden by whatever is in Brightspace. If there's ever a conflict between what I try and clarify in class and what's on Brightspace is right and I'm wrong. All right? Okay. Undergrads, you're working on assignment 3. Any questions about the assignments? Smooth going so far? Okay, awesome. All right, so we're working our way through the basic tools of the trade. What are the technical skills we need to do sort of robotics in general and evolutionary robotics in particular? I've got a couple more slides in lecture 4 on artificial neural networks. A few more things I want to say about ANNs that are specifically relevant to robots, or specifically when you create robots that are controlled by artificial neural networks. We will then spend most of today talking about evolutionary algorithms, which is the outermost Russian nesting doll in our Russian nesting dolls of an evolutionary algorithm that is optimizing virtual robots inside a virtual environment. Okay. So back to lecture 4 for just a few minutes. We ended last time by looking at some details of artificial neural networks that are relevant for robotics. And we finished last time with recurrent connections. Recurrent connections are a particular kind of synapse that exists within artificial neural networks, and they confer a particular function on artificial neural networks, which is the ability to remember. Kind of important. You've all probably seen movies with people with very short-term memory loss or total memory loss. Very difficult to get around in the world if you can't remember anything. So good for neural networks and good for robots. We're going to see a number of robots shortly where it may or may not be useful to have memory. Okay. Okay, I'm going to skip over this. This is just a point that when you add recurrent connections, it tends to make backpropagation of error tricky. We're not actually going to do backpropagation of error in this class. So if you're interested, you can look into it. Last thing I want to say about artificial neural networks is a little bit of terminology. We started this course by distinguishing between trying to evolve intelligent machines and train intelligent machines. Training or learning, this is the predominant paradigm in AI at the moment. The assumption is that someone sits down and creates the neural architecture for an artificial neural network, and then we bring in some training algorithm to tune all these synaptic weights to get the artificial neural network to do what we want. We all saw a pretty dramatic example of the state of the art of this week, right? DeepSeek. They found yet another way to do this even more cleverly and get a slightly smarter artificial neural network. Good for them. Awesome. In this course, we're going to be focusing on not just tuning the synaptic weights of an artificial neural network inside a robot with a fixed neural architecture. We're going to be evolving both the body and brains of our robots. Typically, in artificial neural networks, these training algorithms are a form of supervised learning. Who's heard about supervised and unsupervised, semi-supervised? Okay, some of you have heard these terms before. For those of you that haven't, supervised learning, as the term implies, there is some supervision of the learner's learning in this case. So we've got an artificial neural network that is being supervised. It is trying to learn that, this artificial neural network is trying to learn that when its input neurons receive this pattern of 1s and 0s, it should spit back this set of output values. This is the supervision. We know exactly what the neural network should do, and we take what the neural network did and we compare it against the supervisory signal here, what it should do. As you'll see in a moment when we start to talk about evolutionary algorithms, when we start to evolve robots or artificial neural networks, we're no longer doing supervised learning, we're doing semi-supervised learning. What does that mean? Well, as the name implies, there's some supervision, but it's less less in the sense that the supervision is no longer local. Let's imagine the exact same neural network, but we drop it inside a robot. And the moment we put an ANN inside a robot, the input layer starts to collect values from the sensors. So typically, when we talk about ANNs inside robots, we're going to talk about sensor layers rather than input layers. And the output layer is spitting out values that are interpreted by the motors of the robot. So typically, from now on, when we talk about ANNs inside robots, we're not going to talk about output layers. We're going to talk about the motor layer. Okay. We drop an ANN inside a robot, and we want it, after we all leave, to go about and clean all of the stuff that's left on the floor and put it in the corner. That's what we want it to do. If the robot is here and facing here, and there's a bit of traffic, there's a little bit of trash over there and over there, it's not immediately clear what exactly the motors should do at that point in time. We don't know. As the teacher, we don't know, so we can't necessarily give detailed supervision. Imagine a legged robot that's running around and pushing all the chairs back into a regular pattern after you leave. It's very difficult in a legged robot that's got many more motors than a wheeled robot. Much more difficult to say the robot should move this motor at this point in time to do this. We don't know millisecond to millisecond what every motor should be doing in the robot at every time. So we don't have this supervisory signal to give the artificial neural network inside the robot, unlike in most machine learning exercises. When we're training ChatGPT or whatever large language model, we know exactly what it should do next. When the sentence is, this is a sentence about artificial, we know exactly what the word is that should come next. We already have that word, and if the chatbot doesn't spit out that word, we backpropagate error. That's supervised learning. Very common. Less common is semi-supervised learning, which we're going to be doing in this class. So for those of you that know a little bit about machine learning and AI, and you're trying to map back what we're learning in this class to that, what we're doing is semi-supervised learning. We do have some supervision, which is after the ANN has caused the robot to do whatever it's going to do, we can measure its performance. We want a robot that travels as far as possible. How far did it go? The further it goes, the better. We can then take this error or this performance or this fitness, and we can then try and propagate it backwards into the artificial neural network to change the artificial neural network so that the next time the robot attempts this behavior, it does a better job. Or alternatively, we can evolve the robot's bodies and brains so that some of them, by chance, with the right combination of body and brain, do a little bit better at whatever it is we want them to do. All good? Okay, that's lecture 4. Speaking of evolving, let's move on to lecture 5 and evolutionary algorithms. It's a little bit unclear in the history of computing, but you can make a case that the very first computer program that was ever written in the 1940s, the very first computer program that was ever written was an evolutionary algorithm. It's described, for those of you that are interested, it was written by Nils Barricelli back in the 40s. And there's only a verbal account of what this program did, and Nils and some others described it as a bunch of virtual organisms or creatures running around inside this brand new thing called a computer. Okay, so no matter how you count, the evolutionary algorithms have been around for a very, very long time. The first clearly recognizable evolutionary algorithms came about in about the 1970s, and they've been a common tool in computer science and engineering and math and robotics and some other branches ever since. Okay, so what is an evolutionary algorithm? Not surprisingly, it's an idea that's stolen from evolutionary biology. We just finished talking about neural networks. People that work on ANNs tend to steal ideas and terminology from neuroscience, and we saw some important terminology from neuroscience last time, which we'll use throughout this course. Those that work in evolutionary algorithms, they steal ideas and terminology from biological evolution, and we'll see some of those today. Okay, so a computer scientist reading The Origin of Species, or reading about evolutionary biology, or observing organisms in nature might derive from their observations or what they're reading that evolution is an algorithm. It's a recipe that is followed by pretty much all species on Earth. All right, what is this algorithm or this recipe? You all know how this works. We have not just one organism, but we always have a population of organisms. Another important thing to differentiate evolutionary algorithms from training algorithms for ANNs. Training algorithms are usually working on one artificial neural network. When we're using an evolutionary algorithm, we're always trafficking in populations. There may be some individuals in that population that are more fit or doing a better job at whatever we want them to do than others. There may be some that are worse. Could I get back there? There may be some that are worse, but we always have a population. Okay, within that population, there's some kind of diversity, and some of that diversity better be coming from genetic variation. So we have diversity in form and function. Within a population of birds or humans, no two birds or humans look exactly the same, and they don't behave exactly the same. There's always a bit of diversity. Some of that diversity comes about from environmental factors, but some of it is a result of underlying genetic variation. Given different forms and functions, wherever this population of organisms or machines is operating, some of them are just going to do a better job than others, and some are going to do a worse job. In nature, those that do a particularly poor job to the point where they cannot find a mate, they cannot produce offspring, they die without leaving any offspring. The survivors survive longer, have a longer chance to find a mate, have a longer opportunity to produce and rear offspring. So surprise, surprise, there are little versions of the survivors, and those little versions look similarly and act similarly to their parents, right? And then we repeat this process over and over again for billions and billions of years, and you get, that's it, right? So descent with modification, Darwinian evolution in a nutshell, as explained by a computer scientist. Start with a random population, delete the poorly performing members, make randomly modified copies of the survivors, and rinse and repeat. Okay, that led in the 1970s to people actually writing this down as code. And we're going to see in evolutionary algorithms today, there are hundreds, if not thousands, of different versions of an evolutionary algorithm. So an evolutionary algorithm is the umbrella term for all of this, for this family of algorithms. The most popular one that's out there is the genetic algorithm. What does the genetic algorithm look like? It's a piece of code that generates a bunch of vectors filled with floating point values, like you see here. So we start by generating a population of random solutions. In an evolutionary algorithm, we're not dealing with populations of organisms, we're dealing with populations of something. What is it? It's a population of candidate solutions to our problem. We have a problem, we don't have a solution yet. The problem is when you all leave, we have a dirty classroom. The solution would be an autonomous machine that cleans things up so the cleaning staff doesn't have to, right? We're looking through the space of all possible solutions for good ones. There's an infinite number of robots that we could drop into this classroom that would leave the room in a much worse state of repair than they found it, right? But within that space of all possible robots you can imagine, there is a vanishingly small subset of robots that would actually quickly and quietly and cleanly and efficiently clean the room. A genetic algorithm, like biological evolution, if you squint, it's also a search mechanism. It's searching for candidate solutions. Okay. In a genetic algorithm, we have this population of candidate solutions, and then we also need, we as the human programmers have to give to this genetic algorithm a fitness function. As the name implies, it's a function that takes as input each candidate solution and spits out as an output a number, a fitness. How good is that candidate solution at whatever problem we're trying to solve? The genetic algorithm takes this fitness function and applies it to each candidate solution in the population. In the first generation here, we just have random solutions. It assigns values. You can imagine that randomly generated solutions tend to do very, very badly at whatever it is we want them to do. They all get very, very poor scores assigned to them by the fitness function. But because there's variation in our candidate solutions here, some of them are slightly less worse at the problem than others. Those survive. The others are killed off, and the survivors, the genetic algorithm takes those vectors and makes copies of them and modifies them randomly in some way. In my little cartoon here, this particular value in this parent vector has been changed to 0.5 in this child vector. What is this red value representing? What's the analog in nature? Mutation, right? So you can see we're already starting to steal a bunch of terminology from evolutionary biology. We're stealing the concept of fitness, the mechanism of mutation, and off we go. Okay. This is about as simple as you can imagine. We're going to see some evolutionary algorithms that are a little bit more complicated. The top is biological evolution. The bottom is artificial evolution. If we take artificial evolution or evolutionary algorithms and combine it with robots, or more specifically a robot simulator, we get the field of evolutionary robotics. And you already now know how this works. We create, in this case, not just vectors, but we create a population of virtual robots, where each virtual robot is a candidate solution to our problem. This is a pair of videos from a very old paper I was a part of years and years ago. We were trying to evolve a robot to brachiate or swing from tree limb to tree limb. Primates are particularly good at brachiation. This particular species of primates were not that good at it. Go check out some YouTube videos of gibbons. They are the world champions at brachiation. It's fantastic. Okay, brachiation, you can imagine robots operating on a steel truss or bridges or high rises that are being built. It's not actually a bad strategy for how to get around. We're not looking at a population of virtual robots here. We're obviously only looking at one. This is the most fit robot in the population at this point in our evolutionary algorithm. And it's doing an okay job. It's moving along this beam. And we were particularly interested in this solution as roboticists, because this robot is it's exploiting its physical relationship with its environment. Remember our discussion last week about embodied cognition? One of the good things about having a body in the world is you can exploit it to do a better job of whatever it is you're trying to do in the real world. We are trying to be anti-Cartesian here. The body is not a drag. It's not something that's slowing us down or getting in the way of pure, lovely thought. It helps us. It makes things easier. How has this robot evolved to exploit the physical interaction between its body and the environment? It's swinging its tail back and forth, and you mentioned the M word, momentum. It's exploiting its own momentum. So its tail here, these are its batteries. You can see the physical version of this robot that we built on the right, and there's a heavy battery pack at the bottom. This was work we did in 2002. Batteries were really, really heavy back then, which we were worried about because now we've got a heavy robot hanging from a beam, but it figured out this heavy battery is not actually a problem. It turned it into part of the solution. It's not a bug, it's a feature. Yeah? Okay. We built it. We built this robot, crossed our fingers, and in this case at least, we managed to cross the reality gap. This is something we're going to talk about next month. Not too difficult to evolve robots in simulation. You're in the process of doing that right now. It's nice to get this cool idea of something that looks nice and acts nicely in simulation, but to actually translate it into a physical machine that retains its form and function in the real world, really, really, really difficult. It's probably, I would say it's probably the number one problem faced by roboticists at the moment, the reality gap. Okay. All right. So that's evolutionary robotics in a nutshell. You already know that. Okay. Before we go any further, we're going to pause and introduce some other concepts and terminology that are going to be very helpful when we think more about evolving populations of robots. The theoretical evolutionary biologist Sewell Wright, back in the 1930s, came up with sort of a mathematical thought experiment, not unlike the Chinese room. This is a purely theoretical construct. But when you think about this theoretical construct, it helps you think through a lot of the problems of evolutionary biology. When you put a bunch of animals wash up on a small uninhabited island, after a few generations, you tend to see much more diversity in that smaller population than you saw on the founder population back on the mainland. Why is that? Why are small, isolated populations of things, why do they tend to evolve more diversity than bigger populations? That was a puzzle in evolutionary biology for a long time. You can think about it, maybe come up with some answers of your own, but it's easier to think about the problem itself and potential solutions armed with this particular thought experiment, the fitness landscape. Okay, here we go. The fitness landscape can be a very, very large space. It usually is. It's usually very high dimensional. We're going to start with just 2 dimensions. Let's imagine a hypothetical species, and when you look inside the genome or the DNA of that species, there's one and only one gene. This is why it's hypothetical. That tends not to be the case. Okay, we're going to assume that that gene can take on a bunch of different alleles. If you forget your high school biology, an allele is just the different values or the different types of things that can exist at that gene. Okay, and we're going to imagine for our purposes that these alleles, there's an infinite number of them. They can be any, we're going to represent them with numbers, and they can be organized along the real number line. So imagine either a single gene with an infinite number of possible alleles, or going back to the genetic algorithm for a moment, imagine a population of vectors where every vector is of length 1. Each element in the vector here represents one gene. Assume we're evolving a population of things that have just one gene, and the value of that gene or the allele of that gene can be any floating point value. So far, so good? Okay. So it turns out that there are an infinite number of genetic variants of that species, right? Because there's an infinite number of values that that gene can take on. We could create an infinite set of those organisms, and they would all be genetically unique. So far, so good? Okay, we're going to arrange those values along the horizontal axis of our fitness landscape, and we're then going to observe each of these infinite organisms, and we're going to measure their fitness. How well or how poorly do they fit in their environment? How long do they live for? How many offspring do they produce? How well do they brachiate from right to left? Doesn't really matter. But we assume we have some way to quantitatively measure fitness. For each one of these points, we then plot fitness as a value on the vertical axis here. And if we now literally connect the dots, we get a 2-dimensional landscape. Tell me, this obviously isn't an infinite set. We've got a large number of individuals here, but it's finite. Tell me about the fitness distribution across this hypothetical population.
Certain values of the gene are going to have much higher success rate.
Success rate or higher fitness, yeah? So some individuals are more fit than others. This fitness landscape is not flat. If it was flat, all the individuals would be genetically distinct, but phenotypically the same. So we're going to introduce another term, phenotype here. Phenotype is all the stuff, the form and function that's produced by the genotype. We could have a population that's genetically diverse, But if the fitness landscape is flat, everyone has equal fitness, everybody looks identical, and everybody acts identically, we have a population that is phenotypically homogeneous. So far, so good? You can also imagine a population where everybody has exactly the same DNA, but fitness is how sunburned you are. And everybody goes outside for more or less periods of time. So we've got less and more sunburned individuals, but everybody has exactly the same DNA underneath. Genetically identical, but phenotypically, they look and act differently. So far, so good? Okay, 2D fitness landscapes are super boring, so let's move on to another hypothetical species here that has 2 genes, and we can now travel horizontally in this 3-dimensional space, and every horizontal position in this 3-dimensional space corresponds to a unique set of a unique pair of gene values. And we can then, for each one of those individuals, we can ask about the fitness again. And the more fit that individual with that pair of gene values is, the higher that point is, the less fit that individual is, the lower that point. Tell me about the fitness distribution of this hypothetical species. What are the flat regions telling you?
Like at extreme values of either gene, the expression of the other doesn't really impact the fitness.
It doesn't, right, exactly. So in extreme values out towards the edges here, for extremal values of genes, the fitness landscape is flat, meaning it doesn't matter too much what your genetic values are, or you can change those genetic values a little bit, and your phenotype or your fitness doesn't change. But in this inner region, small steps horizontally, small genetic changes lead to large phenotypic changes, or at least large changes in fitness. So far, so good? Okay. All right. I'm not going to draw a 4D fitness landscape for you because I can't. So you'll now have to do this mentally. As you can imagine, for most real species, they have many more than 2 genes. Still not exactly clear how many we have, but it seems to be around like 30,000. Yeah? So our fitness landscape for Homo sapiens sapiens is a 30,000 plus 1 dimensional space. There are 30,000 horizontal dimensions in this horizontal in quotation marks that you can travel along. You can move out along this horizontal space, which is in 30,000 dimensions, and somewhere in there is you. There's a set of 30,000 alleles that defines you, and your brother or sister and your cousins are probably nearby horizontally. So far, so good? Okay. Fitness, I don't know how you calculate fitness of a human being, but you get the idea, right? Very, very high dimensional space. So whenever we're looking at a biological species, or if we're looking at a population of robots, and we're going to look at lots of populations of robots in this class, we're thinking about how many genes define their phenotype, what they look like and what they do. That's the fitness landscape, and then we have to add 1 additional dimension for fitness. Okay. All right. So armed with this idea of the fitness landscape, we're now going to finish out this lecture by looking at a series of increasingly powerful evolutionary algorithms. We're going to start with an evolutionary algorithm that's actually so simple, it's usually not classified as an evolutionary algorithm, but we're going to start simple. It's very simple. You can code up the hill climber in about 6 lines of code. You can probably do it in less if you're a good coder. Super, super simple to code up, but the hill climber has a problem, and we'll see what that problem is in a moment. Okay, what is the hill climber? The hill climber starts with a population of 1. This is why it's usually not even classified as an evolutionary algorithm. There isn't really even a population. There's a single vector that encodes a candidate solution to a given problem, and we're going to call that vector the parent. There's a single parent out there. we take all of these values and we locate that parent horizontally in the fitness landscape. You can see there's many more than one gene here, but again, I can't draw in higher dimensions, so we'll go back to 2D for a moment. We've got our parent, and we'll assume this parent actually only has one gene. Here's where the parent is sitting horizontally in the fitness landscape. We take this candidate solution and we pass it, or we, the hill climber, passes it through the fitness function, and the fitness function gives back a fitness value for the parent, which tells us how high to place that point in the fitness landscape. Let's assume it lands there. Okay, we have one parent, we know it's fitness. That parent now produces one child down here. And as we're copying the child, as we're copying all the gene values from the parent into the child vector, every once in a while, we make a mistake, or the hill climber makes a mistake and randomly modifies one or a few values in the child's genotype. Because all of the values of the child, all of the gene values of the child are close to the parent, that means that the child is usually close to the parent horizontally, right? Remember, the horizontal position is determined by the individual's genotype. So let's assume the child is sitting right here. It's close horizontally, but when we take the child's genotype, or the child, and we pass it through the fitness function and we get back a fitness value, the child is slightly worse than the parent. What do you think the hill climber does at this point? It has a parent vector, child is slightly less fit than the parent. What do you think the hill climber does at this point?
Does it discard the child?
Discard the child, right? Harsh, but this is the way the hill climber works. We're back to the parent. You can guess what happens next. The parent produces another different single offspring, and we measure the fitness of the child. Let's assume at this point that the child's fitness is slightly higher than the parent. What happens at this point, do you think?
The child becomes the new parent, basically.
That was a very polite way to say it. The child becomes the parent. And now we have a new parent. So again, in the fitness landscape, let's imagine that this second child had landed here horizontally as a result of random mutation. And when we passed it through the fitness function, its fitness was better than the parent. So it's sitting up higher in the fitness space than the parent. We delete the parent, and now the new parent is sitting right here. Why do you think the hill climber is called the hill climber? It's always going up. It's climbing a hill. It's climbing the hill or the slope of local fitness. In this region, wherever it is in space, it's always trying to go up. Yeah? Imagine you drive out, maybe not today, but you drive out on a warmer day to Mount Mansfield, you park your car, your phone's not working, so you don't have GPS, and it's a super foggy day. You should get in your car and go home, but let's assume you don't do that. You get out and you decide to try and get to the top of Mount Mansfield, so it's foggy all around you, you can't see anything. We can see, or I'm showing you this fitness landscape, but from the perspective of the hill climber, it can't see the fitness landscape. If it could, we wouldn't need an evolutionary algorithm. We'd say, there, that's the solution to the problem, right? We don't know what it is. Everything is shrouded in fog. So you're trying to climb Mount Mansfield, you look down and you see if you go that way, you'll have to take a step down. If you go that way, you take a step up. So you take a step up, you do it again, you do it again. Are you going to get to the top of Mount Mansfield in this way? You're not going to move very quickly. I hope you don't move very quickly. Is this going to work? Maybe. Realistically, again, not today, but let's say you went and actually did this. You have to always step up. What might happen?
You could end up in a hill that's slightly taller than that, but if you go down from it, you could end up in a bigger hill. So you could be in a different hill.
You could be in a different hill. Like this particular parent is standing on the slope of this hill. It is not standing on the slope of Mount Mansfield. what's going to happen? What would happen to you in the parking lot on a foggy day with no phone? And what's going to happen to this hypothetical family here that's climbing this hill? It only ever steps up.
When it reaches like the fall summit, it'll think that's the top and it won't go down anymore.
You can keep playing this game. Remember that the children are always close to the parent horizontally. So we're always taking small steps horizontally. They might be randomly generated steps, and then we only take that step if it goes up. Parent, child, parent, child, parent, child, parent, 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 parent. Any child that this parent produces that's close to it horizontally, by definition, is going to have lower fitness. So that child will be deleted, and the parent will keep producing offspring forever. And this particular family has become trapped on a local optimum. This particular point in genotype space is optimal within a local region. Within the global region, this point is optimal. If you go do this at Mount Mansfield, you will not get to the top of Mount Mansfield if you're just taking one step at a time, right? It's not, Mount Mansfield is not Mount Fuji. It's not a cone. There's ups and downs. There's lots of local peaks surrounding Mount Mansfield. This is a huge problem. Remember that everything is wrapped in fog here. So if you run the hill climber and it gets better and better and better, and then it stops and it can't find any better solutions, you as the human programmer or the human observer of the hill climber's operation, what do you conclude from that? Has the hill climber climbed here and got stuck, or has it climbed here and got stuck? It's not just the hill climber that's shrouded in fog. You as the observer are also shrouded in fog. That's why you're running the hill climber. How do you know? How do you obtain a guarantee from the hill climber that it's found the globally optimal solution? The global optimum. How do you get a guarantee from it that it's found the global optimum?
Do you allow it to like step down?
You could do that. Okay, we could allow it to step down.
Would it defeat the purpose if you just like made a whole swarm of these and just set them all to start at different points?
Both good ideas. We'll come back to your idea in a moment. Let's switch to your idea. The hill climber is the simplest sort of evolutionary algorithm you can write. The problem is it gets stuck on local optima, and you cannot obtain a proof from it that it's found a global optima. And in practice, as you can imagine, if you're only ever stepping up and you never step down, and you get started in an unlucky initial position, it gets trapped in local optima all the time. The hill climber is really good at quickly finding mediocre solutions to your problem. Okay, so let's do better. Let's make a slightly more complicated search process. And I'm going to put this little cartoon over here on the left, which is sort of this boiling down of Darwinian evolution into an algorithm. And as we go, or after class, you can visually compare what we talked about to this algorithm, how much all of these algorithms capture this to some degree. Okay, but I'm not going to talk about this explicitly. Okay, so what a surprise. We have this thing called the parallel hill climber, where we generate a bunch of parents at random to begin with. So now we're kind of comfortably in the territory of evolutionary algorithms because we have a population of candidate solutions. Again, because I'm not a very good drawer and I'm a little lazy, let's assume a population of 2. We have parent 1 that landed here in the fitness landscape, and parent 2 who landed here in the fitness landscape, and each parent, as in the hill climber, produces one child, C1 and C2. C1 has lower fitness than its parent, and C2 has higher fitness than its parent, so you know exactly what's going to happen. Wave goodbye to C1 and wave goodbye to P2, and rinse and repeat. Each of those 2 new parents allowed to produce one offspring each, and we keep going. Given this drawing, and given your intuition now about the hill climber and the parallel hill climber, how do they compare? Is this better? Why is this better?
If they aren't like at the same fitness level, you
If they aren't at the same, if they are horizontally quite distant, you could make them meet in the middle. Great term. We'll come back to that in a moment. Doesn't exist in the parallel hill climber. This is it. This is all you get in the parallel hill climber. Is it better than the hill climber?
I mean, you're less likely to get stuck on a single local like maxima, but it's kind of just still like a guessing game if you're actually at the right one.
It's still a guessing game. Actually, all evolutionary algorithms are guessing games, but you're right. The parallel hill climber is slightly less worse than the hill climber. It's slightly less likely to get stuck in local optima. It does something much better. They all get trapped in lots of different local optima, and maybe with a large enough population, one of them will happen to land on the slope of Mount Mansfield. They will land on the slope of, unbeknownst to them, the global optimum, and they'll climb there, and you're good. The parallel hill climber found the optimal solution for you. Most of evolutionary algorithms, all they're trying to do is just manage this problem. No algorithm on the planet yet, including non-evolutionary algorithms, has solved this problem perfectly. Very tricky to get trapped in local optimum because you don't know where the global optimum is. You're just trying to reduce the probability that that happens. Okay, all good with the parallel hill climber? Okay, let's keep going. Some of you have already shouted out heuristics or ideas to further improve things. Let's let them meet in the middle. Let's take the parallel hill climber. So we've got a population of parents. Each parent is going to produce one offspring, exactly like in the parallel hill climber. But every once in a while, when two parents produce two offspring, during the copying of the DNA, as we're making a copy of vector P1 and we're making a copy of vector P2, we're going to cut both child vectors at some position. And we're going to cut them at the same horizontal position, and we're going to take the first part of C1 and glue it onto the back half of C2. We're going to take the front part of C1 and glue it onto the back of C2. I'm describing, I think, what you mentioned, kind of, happens in certain species, including this species. What are we describing? Crossover or sex, right? So mutation and crossover, Mother Nature's main two heuristics for generating diversity in the population. Mutation is sort of local search, right? It's found something that kind of works. It's on the slope of a local optimum. Produce something nearby, right? You have something that's kind of working. Don't reinvent the wheel. Make slight variations to that and see if you can make that solution better and better. Genetic recombination and sex is a more intelligent search algorithm, or a variation, I should say variation operator. It introduces a particular kind of variation into the population. So given your point, what would happen if we had one parent way out here and one parent way out here? And let's assume, again, we don't really know, but let's assume that these two parents, parent one has solved one half of the problem. Whatever the candidate solution P1 is, it's got half of the solution figured out. P2 also actually looks terrible on the fitness landscape here, but let's assume that P2 has figured out also a different part of the problem. Remember our discussion about the exclusive OR neural network last time. For a neural network to embody exclusive OR, it needs to compute AND internally, and it needs to compute OR internally. Let's assume that P1 is a neural network, and it's encoded AND internally, but not OR. Assume that P2 has encoded OR internally, but hasn't figured out AND, right? Okay, there's potential here. In the population, distributed across the population, is a complete solution. The problem is that complete solution is broken up into pieces and is embodied in different individuals in the population. Genetic recombination evolved in nature. Sex evolved, was discovered and evolved because if you do it right, and it's still, and I don't mean non-randomly, if you do it right in the sense that you cut at different places and bring parts together, every once in a while, you'll bring together the best part of P1 and the best part of P2, and that child will be more fit than either parents. It internally encodes and or. Even in P1 and P2 that have part of the solution correct, there's lots of other ways you could slice them and combine their parts that would produce children that are worse. Sex doesn't always work. But it's around, it's pretty common on this planet because even though the chance is rare that you'll bring together the best of both worlds, it does happen sometimes. And when it happens, there's a big jump in fitness. So in my cartoon example here, we have P1 and P2. So here's P1 in red, P2 in blue, and I've randomly cut them at this particular point. I bring together the first two red values from P1 with the remaining blue values from P2, and that's C1. C2, down here, we take the first two values from P2, the blue values, and we tack on to those two blue values the remaining genetic material from P1. Unfortunately for C2, that didn't work. It wasn't a good combination of the partial solutions from P1 and P2, but by chance for C1, we cut in the right place and we brought the and from P1 together with the or from P2. And C1 still isn't perfect. Maybe the synaptic weights that are flowing out from and or are not quite correct. It's not doing XOR perfectly yet, but it's pretty close. And with some subsequent mutations, the descendants of C1 finally get to the top of Mount Mansfield. That's a visual representation of why sex works sometimes. Yeah? Okay. Are we done? The other thing to point is, again, it doesn't always work. When you include recombination, it simply reduces the probability of getting stuck on a local optima. It can still happen. Okay, this algorithm that we just described, this is the genetic algorithm. It's the most common form of evolutionary algorithms out there. It's been around since 1983, 84, something like that. It's been around for a while. Okay. All right, turns out that there are smarter things you can do. So we're going to add another little hack from evolution, biological evolution. This one's a little more subtle. Let's start by we're going to start with the genetic algorithm. The genetic algorithm also still has some problems that can be cleaned up. Let's imagine we have an individual here from the population. This is its set of gene values. It's got sort of intermediate fitness here. And start to think about all of the offspring that could be generated from this parent using just mutation. We'll forget about recombination for a moment. Let's assume the step size is 0.01. Step size is not a very biological term. You can think of step size as the size of the step that the parent can take horizontally. It can step 0.01 to the right, in my cartoon example, or step 0.1 to the left. Step size represents mutation magnitude. If you alter a gene, if you mutate a gene inside the genotype, the step size says sort of, what is the size of the, I'm sorry, I misspoke. The step size indicates the magnitude of the mutation. How much does a gene change when it gets hit with a mutation? Remember that genetic change always corresponds to horizontal movement in the fitness landscape. So large magnitude or high magnitude mutations have big step sizes, move a long distance horizontally. This is something that when we write an evolutionary algorithm, we have to decide how much are you going to alter, where was my example of that? When you mutate a gene, how much are you going to mutate it by? That's something we have to build into our evolutionary algorithm. It turns out that in this case, I chose well. 0.1 is good. Why is 0.1 good? Well, if we're here and you consider all steps to the right or to the left, we've got this horizontal range. And so all of the offspring are falling within this horizontal range. And you can see that within half of the range on this side, half of the children are bad and half of the children are good. That's actually really good odds in an evolutionary algorithm. Half of the offspring are going to be better than the parent. It's not going to take long through random chance to start to climb a slope. Okay. Let's assume, however, that the fitness landscape actually looks like this. This is known as running out of space here. Where's my eraser? This is known as not surprisingly, rugged fitness landscape. What does the ruggedness of a fitness landscape represent? Again, the fitness landscape is a hypothetical idea.
Probably the amount of local optimum.
The amount of local optima, absolutely. This looks scary, right? If you're going to try and just sort of climb local peaks while wandering around in the fog on this mountain range, very unlikely that you're going to get to here. Yeah, lots of local optima. Let's assume by some amazing chance a parent has got to here. It's almost there. Let's say we got Google to give us all its data centers for the day. We just had enough compute. We created a population of 10 million individuals, and off we went, and we got to here. We're actually close. Remember, everything is clouded in fog, so we don't know that we're close. But we have something that's pretty high from everything else we've seen. It's higher than anything we've seen. We've seen a lot of other things get stuck, and this thing is still going. There's a slope here. Okay, we have our step size of 1. So this parent starts to produce offspring that are between 0 and 0.1 units to the right. And it's producing offspring that are 0 or 0.1 units to the left. That's the mutation magnitude, which I've arbitrarily coded into my evolutionary algorithm. Was there a question? No? Within this cartoon example here, which of course I've cooked in my favor, you can see that most of the offspring are going to land on lower slopes. The vast majority of the offspring are not going to work. There is a very, very narrow window in here that if mutations occur at these horizontal coordinates, their fitness will be higher. But it's very, very unlikely. So the step size wasn't a good choice. As a programmer, you should be itching at this point to change something. What is it?
Should the step size be able to be like any number between 0 and 0.1?
Yeah, I think you're on the right track, right? The step size is 0.1 at the moment. So values can change anywhere up to 0.1 greater than the original value and anywhere up to 0.1 less than the original gene value. What do you want to do for this poor parent at this point? You want a smaller step size, right? You want to reach into the code and tune down the mutation magnitude or the step size. But you only want to do that because I've removed the fog for you, right? You know this peak is there. You also know that most of the offspring are failing. So maybe you have a little bit of a sense that you want to make it smaller. But you only want to make it smaller now. If we had made it smaller here, what would have happened? What would happen to this parent if it was operating under a step size of 0.01? It would take 10 times or more to climb, right? We'd slow the climb. So one of the things I hope you're taking away from this is that you can't know what the step size is a priori when this thing starts. And also, depending on where individuals are in a fitness landscape, they may need different step sizes. I've drawn a uniformly rugged fitness landscape, but for real world problems, there are rugged regions and smoother regions. This is a headache. How are we going to decide what the step size should be? There was a great idea, actually this goes back to the 1970s. This became known as the evolution strategy. Very much like a genetic algorithm, we've got our population of genes, but the genotype, which remember is the blueprint, the thing that encodes the phenotype or encodes the candidate solution, is no longer a vector, it's a 2 by n matrix. Every gene value that encodes part of the candidate solution, it has a corresponding value associated with it, which is that gene's step size. We just talked about step size and mutation magnitude for sort of the whole organism or the whole machine. Now we're suddenly talking about individual genes having individual step sizes. Can you make that intuitive using the fitness landscape? What does that mean for a parent that's moving around on a fitness landscape where the genes that make up that parent have different step sizes? How do these different step sizes for individual genes alter how the parent throws out offspring into the fitness landscape?
I mean, it just changes how far it moves in any given direction.
How far it moves in any given direction, in any given horizontal direction, right? Every gene is one horizontal direction in our usually high-dimensional fitness landscape. So if gene 1 has a relatively low step size, then the parent will spit out offsprings within that narrow range along that horizontal dimension in the fitness landscape. Another gene that has twice the step size will throw out offspring twice as far away horizontally along that horizontal dimension. Everybody see that in their heads on a fitness landscape? Okay, so let's imagine now we have a population of these 2 by n vectors. And at the beginning, each of these 2 by n vectors has random floating point values in it. The top row tells us where to put those parents horizontally in the fitness landscape. We compute the fitness of all of those parents, so we know their heights. And then those parents start throwing out individuals closer or further away from them along different horizontal dimensions relative to other parents. Can everybody see this? One way to think about this is imagine you're looking down at the fitness landscape from above and you sort of have a heat map which represents elevation. If you saw the points representing the parents below you on the fitness landscape and you started to see the offspring appearing on the fitness landscape, you're looking from above so you can't see height, or maybe height is color, doesn't really matter. You'd start to see those points, the offspring, landing in an ellipse relative to the parent, right? Where longer axes of the ellipse represent greater step sizes, and shorter axes of the ellipse represent smaller step sizes. Yeah? I've got similar eye color to my parents, but my hair color and style is very different from my parents. Maybe as a child, some of my traits or gene values that encode those traits tend to be closer or further away from my parents. Just to finish this analogy, if you think about this ellipse, we're doing this in 2D now. We're looking down at a fitness landscape in 2 dimensions. Remember, everything is very high dimensional here. So the offspring are being thrown out and land within a hyperellipse relative to the parent. An ellipse that exists in usually very high dimensions.
Is this something that, like, when you were working in evolutionary robotics, you like then try and produce like figures for it? And if you do, how do you do that?
Yes, how do you do that? Typically, we don't try and draw the fitness landscape directly. There's simpler ways to do this. For example, one of the most common ways you're going to do this when you get to assignment, I think it's 7, is you'll start to plot evolutionary time on the horizontal axis. Here's the initial random population of all the parents. Here's generation 1. Here's all the new parents. Generation 2, here's all the parents that existed at generation 2, and so on. What do you think we plot on the vertical axis? You're going to try and represent this evolutionary process that we've been talking about. Absolutely, right? So I might show you the fitness of the most fit parent in the population at generation 0. And then at generation 1, I show you the most fit parent in the population at G1. And if your evolutionary algorithm is working, it usually looks something like this. You might not plot just the most fit parent. You might plot the fitness of all the other individuals in the population as well. Perfectly fine. When it's working, fitness over time goes up. That's the whole point. We're trying to find a fit solution to our problem. If you're lucky, it goes up. Usually it goes up logarithmically. The rate of increase tends to slow down over time. Given what we've said about the fitness landscape, or using the fitness landscape to test your intuitions, why? Why do you think rate of evolutionary improvement tends to slow down over evolutionary time? Absolutely, right? So you go climb Mount Mansfield on a foggy day with an inoperable phone, easy to take steps up, but the further you go, the higher you get, the more likely that when you start to look around you, the only way out is down, right? It gets harder and harder to make improvements. Okay. It's just an inevitable fact of optimization. That's how it tends to go. Okay, so we introduced this idea of step sizes. There's one last detail of evolution strategies that I haven't mentioned, which is the brilliant part. What do you think happens? We've got all these parents that have different step sizes associated with them, that are producing offspring that are more further away or closer to them along different horizontal dimensions. Any ideas? Let's assume we have 2 parents sitting at this point in the rugged landscape. One of those parents tends to spew out offspring far from itself along the only horizontal dimension here. And another parent, which is almost genetically identical to that second parent, it's producing offspring as well, but those offspring are much closer to it. That parent has a much smaller step size than the other parent. What's going to happen? Who's going to end up doing better in the sense of producing more children and more grandchildren and more great-grandchildren?
The smaller step size.
The smaller step size. You can imagine the descendants of that parent that produces more similar offspring is going to outcompete or out-evolve or drive to extinction the descendants of parent 2 or the other parent.
So then, for the areas or dimensions of the landscape that are more rugged, the smaller step sizes are more likely to survive. It evolves towards smaller step sizes in the rugged areas of the landscape.
That's it. You just said it. It evolves step sizes. The first part of what you said is the observation we're making, right? Smaller step sizes in rugged regions or along horizontal dimensions. The more rugged it is, the smaller you should move horizontally. The smoother things are along a given dimension, wherever you happen to be in the landscape, larger step size is better, but we can't know all this a priori. It's too hard. So why don't we turn over the job of determining the best step sizes for different individuals at different places in the landscape to evolution? In an evolution strategy, if this parent produces an offspring, we copy this 2 times n matrix, and we introduce mutations here and here. We alter mutations that land on step sizes does what to that child? To that resulting child? What does it do differently from its parent? Imagine a child that's genetically identical to its parent, except one of the child's step sizes is different from its parent's step size at that gene. How do those 2 individuals behave differently? Yeah, go ahead.
They fit
The fitness, they're identical, right? They're sitting at exactly the same horizontal position in the space and the same vertical position in the space. Those 2 points are sitting on top of one another, but they don't behave similarly. What's the difference in their behavior? The difference is in the way they generate offspring. One of them throws offspring horizontally further from itself than the other parent does. The way in which that parent generates variation in its offspring is different. And depending on where it is, one of those ways of doing it is going to be a little bit better than the other. You can evolve better and better step sizes. Okay, we're almost done with the evolution strategy, but if you've had enough caffeine this morning and you're paying attention, there's a bit of a problem here. Sounds great. We've got something that's pretty smart here. We've got a pretty good search algorithm, except what's the step size for the step size? No one has a good answer to that yet. There are ways to estimate that, to come up with a good way to estimate the step size of the step size, but then what's the step size of the step size of the step size? Yeah? There probably will never be an optimal solution to that problem because of infinite regress. Just for those of you that are interested, going back to theoretical evolutionary biology, you can think of this issue as kind of like momentum, right? So if a parent produces an offspring in this direction, bluer eyes, fairer skin, darker eyes, darker skin, and the amount in which you moved in that direction from the child's perspective was good, keep going, right? If it worked once, it's also likely, generally speaking, to work again. So an evolving population, it looks like, can actually evolve things like momentum. It's able to not know into the future, but it has a sense of how to throw things from one generation to the next. It's not like what you read in the biology textbooks, that there's random variation and random crossover during sex, and it either works or it doesn't work, and nature takes care of the rest. Mother Nature has evolved very, very subtle ways of moving through the space of all possible ways to produce variation or organisms of that type. And it gets very interesting very quickly. Okay, one last thing I forgot to mention before we leave the fitness landscape is sometimes this hypothetical construct is known as a fitness landscape. Sometimes it's referred to as morphospace, and I'll use this term from time to time. When we think about the fitness landscape without the fog, the total shape of this thing, it's really the space of all possible, morpho is Latin for shape, right? It's the space of all possible candidate solutions to your problem. It's the space of all possible machines. There's a morpho space for the planet Earth. There's a space of all possible organisms that could survive on this planet and produce offspring, more or less, in the right place on Earth at the right time. They'd survive, they'd evolve, they'd produce offspring. Despite the gazillions of species that has existed and does exist on the planet at the moment, all of those species occupy a vanishingly small part of morphospace. Kind of an interesting thing to think about. Biology, another way of thinking about this is biology studies life as it is or life as it was. But you can also think about life as it could be. What is the general nature of morphospace? What are all the things that could exist? We're going to spend quite a bit of time thinking about the morphospace for robotics. What is the space of all possible machines that we could evolve? And where in that space are the intelligent, useful, safe, efficient machines? Okay. We've got 5 minutes left. Okay, perfect timing. We'll be able to finish up today. I'm going to show you one more evolutionary algorithm. This isn't it. This is a problem that this evolutionary algorithm we're going to see in a moment was designed to solve. This problem is known as symbolic regression. I'm sorry if this is giving you all anxious flashbacks to high school algebra. You've got a whole bunch of points, and you want to know what is the equation, what is the curve that fits all of these points, and then what is the equation for that curve? Anybody feeling brave? Want to have a go?
By curve, sorry, by curve you mean like a polynomial?
Ah,
I mean, I'm just thinking, I just took numerical analysis, so I was thinking like a polynomial.
Could be a polynomial, could be a lot of other things. Could be a trigonometric function. This is the problem. I ain't going to tell you. What is it? If I tell you it's a polynomial and if it's second order, I'm giving you a lot of hints and the job gets easier and easier and easier. Symbolic regression, we won't go into, regression is the general mathematical problem about trying to find a mathematical expression that describes your data. Symbolic regression is the hardest form of regression. You might not have come across it yet. I'm going to withhold all the symbols. I'm not going to tell you it's a polynomial. I'm not going to give you the polynomial. I'm not going to give you the symbols and ask you to fit the coefficients to the polynomial. All I'm giving you is I want y as a function of x, but I don't know what the symbols are that make up f. I want you to tell me.
It looks kind of like
Y equals x, what is it? Y equals
x minus 3
x minus 3. Okay. Let's do something else. Let's just do something simple. I'm going to guess y equals x. That's the thick black line here. Obviously, not a very good guess. How do I know? I draw the line and then I compute the error here. So all the vertical thin black lines, if I sum up the heights of all these thin black lines, that's the total error of this particular candidate solution to the problem. The problem is I want to find something that describes these points. Here's a candidate solution, y equals x. It's a bad candidate solution because it obtains high error. In this course, we're going to mostly talk about fitness. So high error is bad. We're going to talk about low fitness. This candidate solution has low fitness. Not a good guess. Somebody offered up a much better candidate solution. This candidate solution, x minus 3 squared, is this thick black line here. It's still not perfect. You can see the thin black lines here, but there's fewer and shorter thin black lines here than there is here. Less error here than there is here. Low error is good. Higher fitness is good. We've got two candidate solutions, one with low fitness. We have a second candidate solution that has high fitness. This should start to be looking familiar to you. Let me just jump ahead for a moment. Actually, let me motivate this a little bit more. Turns out this is symbolic regression is a real practical problem. Most of you know the summers here in Lake Champlain. Every once in a while, you get these really nasty algal blooms. They can kill your dog. They can make you very sick. They're not a good thing. No one yet has been able to predict where and when and how much algal blooms will appear in the lake for any given summer. Folks at UVM have been going out on the lake for years and collecting data. Here's the amount of nitrogen at these parts in the lake at this time. Here's the amount of phosphorus, temperature, turbidity, how silted up, how opaque is the water, amount of rainfall, and then how much toxic algae per milliliter was in the water at that place at that time. You can imagine these points, you could plot all of this data as a scatter plot in a higher dimension. And we want to know, is it that the higher the water temperature, the more the bloom? Obviously, it's not. If it was, we'd know what the solution is, and we'd send out boats with anti-algal poisons when we detect high water temperature. We might actually be able to try and mount a proactive solution before a bloom occurs. We haven't been able to do it yet. Some of my colleagues have tried to solve symbolic regression with an evolutionary algorithm, which we don't have time to get into today, so let's put a pin in things here for today. You have a quiz due tonight. You're working on assignments A, 3, 5, and or 6. See you back here on Tuesday. Thank you.